Okay, so as Livia said, this talk, zoom in slightly, is titled something like log geometry and Chow theory. And this is, I guess it's sort of a variant of a talk that I've given on, which has been called log Chow theory, just to try to avoid scaring people off. This talk is going to attempt to explain a bit more about the fundamentals of go into a bit more detail on the two subjects and try to explain more of the basics, since I don't want to assume too much knowledge of either of them. It means that I'll try to give most of the definitions as we go, but some of the definitions, I mean, they're all correct, but they maybe are slightly shorter but equivalent definitions to ones given in standard text, in particular on log geometry. There are some things which make it slightly faster if you simplify these things. Okay, so I guess I want to start off with some sort of motivation, and this is about, I suppose, Chow theory, and really it's about Bivariant theory. So I'm going to recall, for people who aren't enumerative geometers, aren't intersection theory people, what all of this does. So like I said, I guess everything that I'm going to be doing is going to be sort of in characteristic 0, and I don't think that it matters that it's algebraically closed, but somehow all the thoughts that I have about this are really about things over C, and that's, so yeah, where some of the motivation came from for me. Okay, so we're going to start off, and we're going to say, if I give you a scheme X, then we have the Chow groups. So I'm going to write these as being a lower dot of X, and these are, they're in a grade, they're dimension graded abelian group. So graded abelian group. And they consist of cycles on X, so closed integral subschemes of X up to rational equivalence. So consisting of closed integral subschemes of X up to rational equivalence. I suppose yeah. Most people will have seen Phase divisors, and then these just continue sort of Phase divisors down. Okay, so these are and the first thing I want to say is covariant and grading preserving for proper maps. So i.e. I give you f x to y proper, we have a proper push forward map F lower star, and it preserves the grading A lower dot of Y. And their covariant, sorry, their contravariant and what I'm going to say is codimension preserving. For flat maps. So what do I mean by that? Scroll down for a second. So, i.e., given f x to y, which is going to be flat, and relative dimension d, we have a flat pullback. We have a star, a lower dot of y goes to a lower dot plus d of x. So this doesn't quite preserve the grading, but if x and y are pure dimensional, then it preserves codimension. Okay, so Fulton and McPherson in sort of very clever series of papers define something which is the bivariant theory for this. So if you think about these as being, in some sense, homology groups, these bivariant theories are going to be, in some sense, the corresponding cohomology theory. But the analogy is somehow a bit more subtle than that. So what does this mean? So for a map F X mapping to Y, the group, so A upper K, not lower indices now, the bivariant theory of F, this is spanned by the following objects. So it's spanned by collections of maps alpha upper shriek for every diagram. W mapping to V, this maps to Y. This is a Cartesian diagram, so fiber diagram. And where do these maps go? So alpha upper shriek tells you how to go from cycles on V to cycles on W. So I take in some dimensional cycle on V, and what I spit out is a cycle on W whose dimension is decreased by K, where K is the index of this. And you ask that these things be compatible with a variety of different things. So sorry, just to say, to be explicit, an element of this group is one collection of all of these maps. So it's a lot of data specified just by one element. And you ask that these be compatible. And this is where I wish that I had a blackboard rather than rather than just a tablet, because I want to sort of point at things as I go. So you ask that these be compatible with proper push forward. Flat pullback. And intersecting with a Cartier divisor. More generally, what are called Geisen maps. So in particular, it's compatible with taking the intersection of two elements in the sense of intersection theory. Okay, so what, just to again be explicit, saying that they're compatible with proper push forward would say something like, if v to y is proper, then I can take a cycle here, I can pull it back to w and then push it forward to x, since this map would necessarily have to be proper, or I could push it forward to y and then pull it back via the corresponding other map in this collection to get a cycle on x. And the compatible means that those two things have to agree. And similarly, you can form diagrams for flat pullback and for these intersections. And the thing to observe is that these are actually compatible and composable with one another. So, note these are composable. So there's a map, and if I give you a map x to y, and I give you a map y to z, g, I can take a class in here and I can take a class in here, and I can just compose them as diagram, as collections of functions. So there's a map from this to a upper dot. X goes to Z, and this is GF. Right, okay, so we have quite a good handle in the enumerative geometry world on how to construct such elements. And the construction of such elements goes via the virtual fundamental class construction. So, constructing elements of a upper dot, x to y, f, uses, and I guess normally at least, the virtual fundamental class construction. So what does that do? So we embed something which is called the intrinsic normal cone of f, which is the normal cone in the case that f is actually a closed embedding, and in general, if f is smooth, it's somehow a quotient by the tangent, the relative tangent bundle of f, and we embed this into something E. So E is a vector bundle stack. It's not quite a vector bundle, but it's a sort of stacky version of a vector bundle on X. And it's enough like a vector bundle that it has a zero section, and then we intersect the push forward of the class here with the zero section here. So we take, I'm going to write it subscript E, naught E, upper shriek. of the class of this cone. Okay, and the fact this gives you a bivariant class is a theorem of Manolake. So Manolake tells us that this gives you a bivariant class. Right. So that's very good. That's the classical sort of setup of how you do enumerative geometry. And what I want to tell you is roughly, and I'm going to go into more detail afterwards, what do we do in the log world? So in log geometry, so rather than using f as a map x to y, we use some sort of intermediate stack. So we use an intermediate stack so it only depends on y, it doesn't depend on x. So you have x maps to log y maps to y. And really we study something like the cotangent complex and the intrinsic normal cone, and in general the theory of dysmorphism here. But the problem is that this construction of log doesn't interact at all well with taking fiber products. So all of these diagrams won't give you, I mean, they'll give you a class sort of in the bivariant theory of x to log y, but they won't ever, except in extraordinarily trivial cases, give you interesting things in the bivariant theory of x over y. And so that sort of stops, it throws a spanner in the works of all of this machinery from working. In nice cases, log y and y are themselves birational, and that allows you to work around sort of a variety of the issues. But in general, this construction falters at this point. But there's one thing which sort of is interesting. So this map, log y to y, is what's called log. It's logital, it's log smooth. So that in some sense, that's what's responsible for this birationality, in the sense that if you have you don't know about log structures in either case, this actually will just be a birational map. And then there's a theorem, again due to Fulton and McPherson, so theorem Fulton McPherson. So I always miss out the P in McPherson, which is, I mean, it's roughly called, it is called Poincare duality. It takes a bit of meditation to work out why it should be called Poincare duality, why it's the correct statement to make. But it is, and it's very, very nice. What does it say? So it says, given F, a map of schemes, X to Y, so map of schemes, and G, Y to Z, a smooth map of relative dimension D, then going back to this composition map that we had wherever here, there's a canonical element inside here, which is pullback along the flat map G. Then, and the claim is that that map there is always an isomorphism. So then the map A upper dot X to Y, this map is F. This is composed with pullback along G to define a map inside, and it shifts the degree down by D to give something inside the bivariant theory of X relative to Z. This is an isomorphism. Great. So why is this relevant? Well, we really actually do genuinely know how to construct obstruction theories and virtual fundamental classes for this map here. So if this statement were true, but I replaced smooth with log smooth, or even just this log étale, then I could actually just descend the construction that I already have along this map. I'd compose with this thing, which is sort of birational. In nice cases, it's a birational map. And I'd end up with something actually in the bivariant theory of X relative to Y. Okay, so that's sort of the motivation as to why you would want such a thing. Here's the problem, of course. If I just tried to do it with, if I didn't know any log geometry and I just tried to run this with the regular Chow theory, if I translate all of the implications of such a statement into toric geometry, it would say that the Chow groups of a toric variety are invariant underperforming toric blowups. And take P2, blow up a zero-dimensional toric strata inside P2 to convince yourself that that's just not true. Okay, so now we get to the point of the talk. This is like section 2, which is entitled, so what is a log scheme? Okay, so I'm going to start off and we're just going to say what, I'm going to answer your question. So a log scheme X consists of the following data. And so the first piece of data is an underlying scheme. And because we like puns, we're going to write it as the underlying scheme. The second thing is a sheaf of monoids. And although I'm going to say it out loud, I'm not going to write it down. This is a sheaf of monoids in the étale topology, not the Zariski topology. But the distinction between the two doesn't really matter so much. For most things that you think about it as being in the Zariski topology. And a map of monoids, so a map of sheaves of monoids. Sheaves of monoids, alpha x, and this goes from mx to ox star, oh sorry, not ox star, to ox, such that if I restrict this to the inverse image of the invertible elements inside ox, so that then maps, of course, to ox. This should be an isomorphism. Okay, so one particular part of that is, so we can talk about a sort of auxiliary sheaf. Oh, sorry, I should have said this is a sheaf of finitely generated monoids. So we talk about, So we can talk about another sheaf, which I'm going to write as being m bar x, which is mx, modulo the image of ox star inside it under this isomorphism. Whenever I draw pictures, I'm actually really going to draw the stalks of this sheaf, because the difference between m bar x and mx is some data about line bundles and so on, which is quite hard to keep track of. The m bar x is the thing that really you can understand. Okay, so I should also tell you a map of log schemes. X to y is, and it's the following data, to the end of a page, just the page. Map of log schemes, x to y, is a map of underlying schemes. And 2, a map f upper sharp, and fitting into the following diagram, So I have F as a map of topological spaces, so I can pull back. This decided to do that. Oh, I don't mean to do F inverse there, I just mean to do mx. And here is alpha x, here is F inverse of alpha y. This map here is the pullback map on functions, and you ask that you have F upper sharp fitting into here, such that this is a commutative square of sheaves on X. And one part of this, one thing that this gives you is a map also on these M bar sheaves, on these characteristic sheaves. So this gives a map F inverse of M bar of Y goes to M bar of X. So we say F is strict if this is an isomorphism. Okay, so that's given you some data about what log schemes are, and the sort of common, so this is very sort of broad in general, but a particular type of log scheme that people really like, everyone should really like, are FS log schemes. And in order to introduce those, I first need to say that there's a natural example of these things, which are toric varieties. So toric varieties so have a canonical log structure. Given by so first of all, I need to tell you that there's a map from So first of all, we're going to choose P, which is going to be a finitely generated integral, let's say saturated monoid. Then there's a canonical map from P bar goes to the structure sheaf on the associated toric variety. What does this do? So I shouldn't say P, there should be a P there. So this sends an element P, section P inside P bar, just to Z to the P. So this thing isn't quite a log structure because it doesn't obey this statement about being an isomorphism on invertible elements, but there's a way to fix that, which is just to take the push out with the invertible elements. So so the log structure P underline direct sum over alpha P inverse O spec. This is of course quite hard to write. Spec K adjoint P star is a log structure. Okay, so if I wanted to draw such a thing, and I'll just draw it for case of A2, and I'm just going to draw the stalks of this M bar characteristic sheaf, ghost sheaf. What I see is along the toric boundary, I'd see an n everywhere, apart from at the origin, where I'd have an n squared. This is a nice example to think about and work with. So there's a class of log structures which are called FS log structures. So definition, X is FS. If etal locally, we have charts. So I'm going to just draw a diagram and then say, so U is going to be an etal open set. Since it's etal, it carries a canonical log structure because M is a sheaf in the etal topology. The conditions are etal local. This should emit a map CH. The spec K adjoint P. P is again, it's going to be a finitely generated, saturated integral monoid. And we ask that CH be strict. So it's really saying, in some sense, that the log structure on X is locally looking like the log structure on a toric variety. Right, so I said that one consequence of what we'd want if we wanted to prove a statement like this Poincare duality would be that we'd need to understand what happens as I subdivide fans of toric varieties, as I blow up toric ideals on a toric variety. And that translates across very well to this world of log schemes. So there's a definition. It's due to FCarto. So F X tilde to X is a log blow-up. So this is sort of the replacement of subdivisions of fans. If locally everywhere, so locally on X tilde and X, we have diagrams. So X tilde is going down to X. This is our map F. we have a chart. Yeah, we'll say like this. We have a chart for x tilde. We have a chart for x. And this is mapping to spec K adjoint P with its toric log structure. Now I can take this and I can blow up a toric ideal inside P. So this is the blow up at I spec K adjoint P. So I a toric ideal. K adjoint P. So in particular, this thing is already a toric variety, so it has a canonical log structure. So it makes sense to ask that this is strict and this is strict. And ask that this is a pullback. Right, so this sort of generalizes the idea of refining fans in toric geometry, is what I want to say. Okay, so there's what we want is that, so this is giving us sort of local charts, and what we want is that these charts are particularly nice. We want that this map here be a map between two smooth spaces, because in that case, there's already a recipe for how to construct a pullback Gaussian map or a bivariant map for that. So here's a lemma. P, sorry, spec K adjoint P is smooth if and only if P is isomorphic to n to the r for some r. And this, in fact, is equivalent to, if I look at the stalks of this characteristic ghost chief m bar, this should be isomorphic to n to the rp. So this is allowed to vary as I move p around. In the particular case of A2, you can see it's either 0, 1, or 2. So that makes sense to make the following definition. This is like a long series of definitions. So define x as locally free if the stalks m bar x at x is isomorphic to n to the rx, so it's allowed to vary as I move around, and f x tilde to x is a locally free blow-up if f is a log blow-up and x and x tilde are themselves locally free. Okay, so I can now introduce what the gadget is, but first I want to draw a diagram and give an example. So why is this a useful property to have? Well, it's saying, so here I have x tilde, here I have x. It would be saying that what I have are charts between an and a smooth blow-up of an. I'm going to call this map FP. So FP has sort of a canonical bivariant class, which is the Gaussian map, which is just pullback FP upper shriek, and it's contained inside the relative degree 0 part of this bivariant theory. So what does this do? I just say if I have a cycle here, I move it to be transverse to all of the things that I'm blowing up, and I take the inverse image, and that's well defined, which is very easy to understand process to do. And if you're careful, you can see that actually all of these glue together to give you a map. So these glue to f up a shriek, and it's contained inside A0, x tilde to x. Great, so I said that I wanted to give you an example. So here's the example, which makes clear how these charts come into play. So I'm going to take A2 with its standard log structure. And I'm just going to take the origin, and I'm going to take an induced log structure on it. So here, mx is just k star direct sum n squared, and the induced map, if these two are both 0, sends it to the element of k star here, and if either of these are non-zero, it gets sent to 0 inside the structure sheaf. Okay, so I blow this up at the origin. I take the fiber product. I haven't told you how to calculate fiber products of log schemes, and in general they can be different. They are different from fiber products of underlying schemes, but in this case it's not. What you get is P1, but this P1 has sort of a slightly strange log structure. It generically everywhere has an n, apart from at 2 points where it has an n squared. Okay, and so the pullback map that you get in this case preserves degree, so it's not the flat pullback taking a point here to the fundamental class of P1. It takes a point here and it pulls it back to just a point inside P1. So the log structure is picking out for you the correct choice of Gaussian map to pull back along. Okay, so here's then the definition of the gadget, so, which is, I guess, called the log Chow groups. So a lower dot, upper dagger of x. It's the direct limit, it's the co-limit over all x tilde going down to x, x tilde locally free. So this gives you some objects in a category, and I want to take all log blow-ups between them. So that would be all locally free sort of covers of x between them. Okay, so this defines for you some collection of groups, and the claim is that this has all the properties that you would want. I want to make one statement clear, is that this gluing here is actually functorial with respect to different composition of blowups. So this is actually a well-defined thing. There's a lot of checking on dependence on choices that I'm sort of sweeping under the rug here. So the claim is that this has all of the sort of properties that one might want of proper push forward and flat or log flat pullback. And I want to say that it does have all those properties, but I want to make it also clear that you actually have to take a little bit of care. So section 3.
Sorry, can I ask, it's a limit of what?
Sure.
You said direct limit, but of which things?
So over the category whose elements are x tilde mapping to x, a log blowup,
So do you take a dot of those x tilde or something?
Yeah, you take a dot of those x tilde and then you pull them back along. So the maps between them are the Gaussian maps associated to the associated blow up. And since these are inside A0, they preserve dimension. And so they preserve the grading on a lower dot. Does that answer the...
Yeah, thank you.
Yeah, cool. Okay, so I want to say that you just have to take care.
Sorry, there
sure.
was a question in the chat a few minutes
Yeah.
ago that was whether I think the log blow up was due to Kazuya Kato. I don't know. I think probably the but
yes, maybe it is due to CovariantPreserving.
It is.
It is. Thank you. So yeah, so the next thing that I want to talk about is due to FCarto. So yeah, I think I transcribed incorrectly which one was due to which. So it's good to catch up. Okay, so you will need to take care with push forward. etc. Sort of, you need to take care with essentially everything. So there's a clever calculation. If I take this P1 with this funny log structure mapping down to a point, there's actually a Cartesian diagram. So P1 mapping down to this thing with an n squared, P1. If I take the fiber product of this diagram in the log category, log fs category, I actually just get back the thing that I started with. There's no change. And so if you were to naively attempt to define push forward, so these two, I mean, everything here is a log blow up, but in particular, these two maps are log blow ups. If I take the fundamental class here, I push it forward and then I pull it back, I get something different. So these other maps are all the identity. I get something different from if I pull it back along the identity and then push it forward along the identity. So you need to take some care. It's not just that you can take the standard push forward. And the problem is one of integrality, which is a sort of common theme in log geometry. So this does not commute using the naive definition, push forward definition. And I guess I was going to define what it means for a map of log schemes to be integral, but we maybe want some time at the end for questions. But what I'm just going to say is it's because the map P1 to n squared is not integral. Thankfully, there's a way to save this. So there's a theorem. Now, this is due to FCarto. And it says that given f x to y, which is a logomorphism, so we can find a diagram we have x, we have y, we have y tilde, we have x tilde. Right, so this isn't, as stated, this is the theorem. Once I fill in this due to FCarto, you need to actually extend it slightly for what we want. You need something which lives over here. So here you have f, here you have f tilde. Let's call this map pi y, and let's call pi y tilde, pi x bar, pi x tilde. So you can arrange it so that f tilde is integral, and all of these pi's are log blowups. And now, if I wanted to define push forward, I could do it by chasing around the following diagram. I have a cycle on X. I pull it back via, sorry, I don't mean to say, this should say that pi X and pi Y tilde and pi X bar are log blowups. Pi X tilde is not necessarily a log blow-up. Then right, so if I had a cycle on X and I wanted to push it forward to Y, I instead should do the following thing. I pull it back along the Gaussian map for this pi X bar. I push it forwards. I should have said that this is also a pi X hat. Sorry, I slightly rushed the end of this. This map, this map, this map are all log blowups. So I push along a proper map, I push along a proper map, and actually, in fact, I shouldn't push all the way down to Y. I should just be content to live on Y tilde. And this gives me a map between cofinal collections inside these categories. And so this gives you a well-defined, after you check everything, map pushing forward from this direct limit associated to X to the direct limit associated to Y. So similarly, you have to take care for flat pullback. You have to take care for taking intersections with Cartier divisors. But in the end, you can recreate all of the tools that you need for doing intersection theory, and in particular, the proof of the Poincare duality statement is just a de Visage argument to get down to working over a point, together with formal properties of all of these maps. So in particular, this also holds automatically. And so the upshot is that you can, so long as you're happy to use these classes rather than necessarily elements actually in the Chow group, there is a sort of functorial, well-behaved way to pull back cycles from Y to X with all the properties that one could hope for. Okay.